Whether you're a bioprocess engineer hunting for the perfect scaled-down model, a biotech founder architecting the leap to commercialization, or a scientific analyst who craves raw technical truth, you've reached the technical edge. In this space, we live by a single mantra: the process is the product. Welcome to the Biomanufacturing and Fermentation Technology podcast with Prasad Ernala. Hit subscribe and ring the bell to join a global community and stay at the vanguard of biotech translation. Let's build the bioindustrial future together.
Welcome to the debate. Today we are digging into what I consider the absolute frontier of bioprocess intelligence. We're talking about upstream digital twins. Now, on paper, this concept is the dream. It is the holy grail of manufacturing. You fuse Raman spectroscopy with off-gas analysis. You estimate biomass and specific uptake rates in real time. You run model predictive control to hold the culture in a perfect metabolic state, preventing overflow metabolism before it even starts. It is, the promise of perfect control.
And then you scale up, and that beautiful, pristine lab model just collides with physical reality. The first time your 10,000-liter vessel hits an oxygen transfer ceiling, or you get a massive foam event that blinds the sensors, that sophisticated state estimator starts hallucinating. It thinks glucose is low, but actually your probe is just fouled. It thinks you're optimizing, but you're actually driving the process right into a crash.
And that is the tension we are navigating today. The core question is this: when oxygen transfer limits hit and mixing gradients appear, does the digital twin provide necessary intelligence, or does it just generate optimism bias? I'm the advocate, and I'm arguing that upstream fermentation is now way too complex for manual control. The only way to close the loop on critical variables is through rigorous digital twins that combine soft sensors with mechanistic physics.
And I'm the dissenter. And I argue that these twins often fail because they assume a clean, homogeneous world that just doesn't exist at manufacturing scale. When the physics change dynamically and the sensors drift, a twin that doesn't know its own limitations it's dangerous.
Okay, so let's start by setting the stakes here. Why are we even having this debate? Why spend millions on these models? It's because the days of set it and forget it in upstream processing are dead. We have to be honest about the limitations of how we currently run these massive bioreactors. We rely so heavily on offline sampling. Taking a sample, running it to the lab, waiting 4 hours for a result, that is just laggy data.
It is laggy, sure, but it's real. It's a physical measurement.
But in that 4-hour window, the biology has completely moved on. Small errors in feeding or aeration, they don't just cost us titer or yield. They change impurity profiles, they shift cell morphology, they trigger stress responses that downstream processing simply cannot fix. We have reached a point where we cannot control what we cannot observe in real time. The digital twin is the attempt to turn the lights on.
Look, I agree with the premise that flying blind is bad. We all want the lights on. My issue, though, is with the hubris of thinking we are observing the process just because a mathematical model says we are. You're talking about closing the loop, letting the computer make decisions on feeding and gassing. But in manufacturing, the priority isn't just optimization, it's survival. The academic literature, it proves these twins work on clean data sets where nothing breaks. Manufacturing is about surviving bad data, regime changes, and equipment limits without creating a quality deviation.
But that is exactly why we need the twin. We need to estimate the states that actually matter to the cell. I'm talking about the oxygen uptake rate, or OUR. I'm talking about redox pressure and substrate uptake. You can't stick a physical probe in for all of those. The integration of soft sensors with mechanistic physics modeling the media, the feed, the metabolism, that allows us to hold the culture in the right state. If we don't have that model, we are just reacting to pH spikes that happened 20 minutes ago.
Reacting late is a problem, I grant you. But flying with a broken instrument that tells you you're flying straight is worse. It gives you this false confidence. And that leads us directly to the first major battlefield of this technology: soft sensors. You view them as these sophisticated state estimators. I view them as the dominant failure point in the entire digital ecosystem.
I think that's a pretty cynical take on what a modern soft sensor actually is. We aren't just, guessing numbers here. A soft sensor is a hardware sensor paired with a rigorous mathematical model. We are seeing methods now like unscented Kalman filters, or UKF, becoming the standard.
Okay, let's pause there. Explain the UKF, because to most operators on the floor, that just sounds like a black box that spits out numbers.
Sure. So think of a Kalman filter as a logic engine that separates signal from noise. It takes the noisy input from your physical probes, like dissolved oxygen or off-gas readings, and it compares it against a model of how the biology should be behaving. It updates its estimate of the true state by balancing the measurement against the prediction. It allows us to calculate things we can't physically measure, like specific oxygen consumption, QO2, in real time. When direct online measurement isn't possible, this is the only practical way to get that visibility.
It sounds robust in theory, it sounds elegant, but the reality we're discussing highlights the flaw explicitly. The soft sensor lives or dies by its inputs. In a lab, you calibrate your probes, you have clean lines, you have time. At scale, you have probe drift, you have analyzer lag, you have fouling.
Which happens, of course.
It happens constantly. And here is the danger. If your dissolved oxygen probe drifts by 5%, or your mass flow controller for the feed is slightly off, that unscented Kalman filter doesn't know the hardware is lying. It assumes the data is real. It adjusts its estimate. It tells you the metabolic rate has changed when it hasn't. It hallucinates a biological event to explain a mechanical failure.
But that's an argument for better sensor maintenance, not an argument against the digital twin. You can't blame the math for a bad probe.
You have to blame the system design. It's an argument that the twin lacks lifecycle reality. Engineers underestimate that a soft sensor needs the same lifecycle governance as a physical instrument. It needs verification, drift checks, outlier handling. It needs a defined ignore me mode. Most twins I see are designed to always give an answer, but when a reactor moves into a regime the model hasn't seen, like a massive viscosity shift or severe oxygen limitation, the model should stop guessing. Instead, it usually confidently predicts a fiction.
I think you're conflating bad implementation with the fundamental technology. Of course you need outlier handling. If the input is garbage, the output is garbage. But the solution isn't to abandon the estimator, it's to strengthen it with data fusion. And this brings me to our second point, PAT fusion. We aren't just relying on one drifting probe anymore. We are fusing Raman spectroscopy, near-infrared, off-gas analysis, and base addition profiles into a unified inference of the state.
Unified inference is a great buzzword, but let's look at the mechanics of failure again.
The mechanics are sound. If you have a hybrid approach, where you use simple online variables, aeration, stirrer speed, off-gas CO2, and you cross-reference that with complex spectral data from Raman, the model can correct individual sensor errors. If the DO probe drifts, but the Raman and off-gas show stable metabolism, the model can identify the conflict. The data conflict becomes noise that the model smooths out to find the truth.
That's a compelling argument, but have you considered that sensors at scale rarely fail independently? They fail in correlated ways.
How so? Give me a scenario.
Okay, take a standard intensified fed batch run. You have a gas analyzer that starts to drift because of moisture in the line, a common issue. At the same time, your controller sees that drift and retunes or shifts the aeration strategy to compensate. Now you have two signals, the analyzer and the controller action, telling the consistent but completely wrong story.
That is a difficult edge case, I admit.
It's a common case. Or consider when Raman says one thing and the off-gas analysis says another. Your fusion model often tries to smooth that over as noise to give you a clean line. But in operations, that disagreement is the most valuable thing you have. It is a signal. It's a screaming alarm that says warning, fouling, or warning, condensation, or warning, physiological transition.
I agree that persistent disagreement should trigger an alarm. But you cannot deny that PAT fusion moves us from simple signal reading to diagnostic logic. We are trying to distinguish between a sensor glitch and a metabolic shift. Without fusion, you have zero chance of doing that. With fusion, even if it's imperfect, you have a probability cloud that is far more accurate than a single offline sample taken yesterday.
I'll concede that fusion is better than single-point failure, but only if the system is designed to treat conflict as a diagnostic finding. not just a math problem to be minimized. The twin needs to say, I am confused, not here is the answer.
Fair enough. Well, let's move to where the rubber really hits the road, where I suppose where the impeller hits the fluid. Mechanistic physics. This is where the digital twin becomes scale-aware. This is the antidote to your concerns about the clean lab versus dirty plant problem.
Is it? Or is it just a more complex way to be wrong? It is the bridge. If we only use statistical models, just looking at correlations, I would agree with you. They don't scale. But the mechanistic twin models the physics. It models KLA, the oxygen transfer coefficient. It models mixing time and heat removal. It links these physics directly to the phenotype of the cell. This allows us to predict how a feed strategy that worked at 2 liters will behave at 10,000 liters. We can predict oxygen transfer limitations before they happened.
I come at it from a different angle. I see a lot of mechanistic twins that are actually just using placeholders. They plug in a single static number for KLA. They assume one mixing time. But you know as well as I do, in a real high-density fed batch run, the viscosity changes, the rheology evolves.
Sure, as cell density increases, the broth gets thicker.
Exactly. And foaming. Foaming and anti-foam addition fundamentally alter the gas-liquid mass transfer during the run. If your mechanistic model assumes a static KLA, it's wrong by day 3. You're predicting an oxygen transfer capability that simply isn't there anymore because the fluid properties have changed.
Well, advanced twins use computational fluid dynamics, CFD, compartment models to capture those gradients. We aren't assuming a static tank anymore. We break the tank down into zones to understand the hydrodynamics. We know that the bottom of the tank behaves differently than the top.
Some do. Most don't. And even with CFD, there is the massive issue of homogeneity. The twin generally assumes there is an average substrate concentration that the cell sees. But at scale, the average doesn't exist for the individual cell.
You mean the gradients?
I mean the journey. The cell is traveling through zones. It experiences excursions, high glucose near the feed pipe, starvation in the stagnant zones far from the impeller. These excursions, they alter biokinetics. They trigger stress responses. Unless your mechanistic model explicitly accounts for that heterogeneity and how it impacts the phenotype, it is over-predicting the safe operating space. You are modeling a happy cell in a perfect bath, while the real cell is riding a roller coaster.
That is a valid critique of static models, but it ignores the progress in reduced order models that run in real time. We are getting better at mapping those gradients. But I want to pivot to why we are doing this modeling. It's not just to watch the process, it's to control it. And this leads us to advanced control and model predictive control, MPC.
Ah, the optimization trap.
It's not a trap, it's precision. Look at overflow metabolism. This is the classic problem. In E. coli, for example, we know that acetate excretion, which is toxic to the product, happens when the specific glucose uptake exceeds the respiration capacity. The cell eats faster than it can breathe. It's a critical threshold.
Right, the critical flux.
Exactly. An MPC system can actively maintain the flux state right at that optimal edge, maximizing growth without triggering overflow. It manages the redox potential dynamically. It feeds exactly as much as the cell can handle and no more. A human cannot do that. A PID loop cannot do that.
And that is exactly why it is dangerous. Optimization at scale is often interpreted as push as hard as possible. When you use MPC to push a process to the very edge of its metabolic capability, riding that line between growth and acetate formation, you are living one sensor drift away from a crash.
But if you don't push, you are leaving yield on the table. You are extending runtimes unnecessarily.
I would argue the value of MPC isn't in optimization, but in containment. It works best when it enforces conservative, safe operating windows. It shouldn't be asking, how fast can I feed? It should be asking, if I feed this fast and my KLI is 10% lower than I think, do I crash the tank?
That's an interesting distinction. You want it to act as a governor, not an accelerator.
It's critical. If the model is wrong, say it underestimates the CO2 stripping limitation, the controller will drive the process straight into a wall. You mentioned constraints, but engineers underestimate the degrade to safe behavior. When the model realizes it's confused or constraints are violated, does it default to a safe, known feed profile, or does it try to math its way out of the problem?
Ideally, it has a fallback. We can tell the controller, maximize uptake, subject to dissolved oxygen remaining above 20%. It is the only tool that can balance competing constraints in real time.
In theory, yes, but practically, implementation reality bites back. You mentioned CO2 there, and that touches on our final area of debate, the blind spots. What is the twin missing?
Every model has blind spots. We are mapping the world, not recreating it atom for atom.
But some blind spots are bigger than others. It's usually the messy stuff, CO2 stripping, foam, and regime switching.
I acknowledge that CO2 stripping and back pressure are often underestimated. As reactors get bigger, the hydrostatic pressure changes. The weight of the water itself creates pressure at the bottom. This changes CO2 solubility, which impacts intracellular pH. But we are seeing more models that include the impact of dissolved CO2 on physiology. It's a solvable physics problem.
It's solvable if you respect it. But look at foam. In most digital twins, foam is treated as a side signal. Maybe it triggers an anti-home shot. But physically, foam changes everything. It changes the holdup, the amount of gas trapped in the liquid. It changes the mass transfer area. It blinds sensors. If your data fusion ignores the fact that the headspace is full of foam, your OR calculation is garbage.
That's valid. Foam is a chaotic variable. It's hard to put an equation on a bubble bath. But what about regime switching? I think that is the more fascinating physiological challenge.
Exactly. This is where biology fights math. Overflow metabolism isn't a smooth dial, it's a switch. You cross a threshold and the cell changes its machinery. It turns on different genes. It's a regime switch.
Right. It's discrete, not continuous.
And most twins try to model biology as a continuous curve. They love smooth lines and gradients. But if the twin doesn't recognize I am now in a different metabolic regime, it becomes useless. It's trying to fit a square peg into a round hole.
I agree with you there. The twin must be state aware in terms of physiological regimes, not just continuous variables. It needs to know I am in growth phase versus I am in production phase. But this brings me back to my core argument. The complexity of these regimes, the switch from respiration to fermentation, the impact of CO2, the gradients, this is exactly why we need the digital twin. A human operator cannot calculate the specific uptake rate relative to the respiratory capacity in their head while adjusting for back pressure.
No, they can't.
So despite the flaws, despite the calibration needs, the digital twin is the only path forward. We refine the models, we improve the sensors, and we use the physics to close the loop.
I'm not saying we shouldn't build them. I'm saying we shouldn't trust them blindly. A human operator might not be able to calculate the QS in their head, but a human operator knows when the tank looks wrong. A human operator knows that if the mass flow controller was just replaced, the reading might be suspect. The twin lacks that context unless we explicitly build it in.
Then let's talk about how we build that context in. If we look at the design review of these systems, what is the ultimate test?
The ultimate test is designed for failure. If I were auditing a facility's twin, I'd ask, what happens when the inputs fail? Run the twin through a deliberate oxygen limitation event. Feed it data from a drifting probe. Does it fail safely? Does it alert the operator? Or does it confidently optimize you into a batch loss?
I accept that challenge. Validation under constraints is key. And I would add, the test is also regarding model portability. If you train this on a 2-liter reactor with high KLA, I want to see the evidence that the parameters hold up when mixing is slow and gradients are high.
Precisely. Tech transfer is where the homogeneity assumption breaks. If the twin doesn't account for the fact that cells at the bottom of the tank are starving while cells at the top are feasting, it's not a twin of the process. It's a twin of a process that only exists in a computer.
I think we are converging on a critical realization here. The goal isn't a perfect twin that replaces the operator. The goal is a twin that acts as a navigation system, one that knows the map, but also knows when the GPS signal is lost.
That's a fair analogy. And to extend it, you don't drive off a cliff just because the GPS says there's a road there. You look out the window.
So where does this leave us? I look at the trajectory of the industry, and I see the inevitable integration of these systems. The demands for tighter, for quality consistency, for speed, they simply require more intelligence than a PID loop can offer. The dream is difficult. but it is necessary.
And I look at the trajectory and see a painful period of disillusionment unless we change the philosophy. We need to stop selling optimality and start selling insight. The most valuable thing a digital twin can do is not to squeeze out another 5% of titer. It's to tell me, hey, your sensors are disagreeing, and I think we are drifting out of the safe window.
I can agree with that. The value is in the robustness. If we can use mechanistic physics to define those safe windows and use soft sensors to track our position within them, we have achieved something huge, even if we aren't perfectly optimizing every second.
Right. The twin should be a tool for containment. It keeps the process in the green zone. It doesn't try to redline the engine.
To summarize my position, upstream processing is colliding with physical limits. We cannot navigate those limits with blind trial and error. We need the mathematical framework, the soft sensors, the PAT fusion, the rigorous physics, to see the invisible variables like OUR and uptake rates. That is the only way to ensure quality by design.
And to summarize my position, the math is only as good as the reality it represents. At scale, reality is messy. Sensors drift, gradients form, and physics change. The best digital twin isn't the one that predicts the most complex future. It's the one that stays honest about the current data quality. It knows its own limitations and knows when to shut up.
It seems we both agree that the era of assuming the lab model applies perfectly to the plant is over.
Absolutely. Reliability depends on safe operating windows, not pure optimization.
And perhaps that is the ultimate intelligence, knowing what you don't know.
Couldn't have said it better myself.
Thank you for joining us on The Debate. We hope this discussion helps you look at your own facility's optimism bias with fresh eyes. Until next time.
Hi there, thank you for staying with me until the very end. If these technical insights help bridge the gap in your own process, please hit subscribe and make sure to hit the notification bell. Stay connected for our next deep dive into the realities of biomanufacturing. I am Prasad Ernala. Thanks for listening.